Welcome back to the video lecture series for the subject Probability Theory and Stochastic Process. Today, we are going to discuss about random process. In this random process, last class, we discussed about distribution function for random process, giant distribution function for random process. So today, we are going to discuss about the density function, giant density function of a random process. Now you consider here, we know all of you, this giant density function, fxy of x comma y, it is the giant density function. Now that is previous concepts of a random variable. Now, if it is apply for a random process, the main difference between random variable and random process is random variable is not a function of time. Whether coming from random process, it is a function of time. So whatever the formula, giant density function, giant probability density function formula, that is going to be right here with function of time. That is the only change between giant density function for random variable, giant density function for random process. Now you see here the formula, the giant density function for a first order probability density function. If you see the first order density function, fx of x1 comma t1. So previously in the random variable, there is no this time. Now coming for random process, we are considering this time. In that random variable, at a particular time instant, we are defining this probability density function is equal to derivative of probability distribution function with respect to this x. Because at time t1, we are considering the random variable. In that random variable, the event is x1. It is the corresponding probability density function. Now, if you apply this concept for second order joint density function. So whenever the second order density function, if you consider whatever the random variable, in that random variable, we are going to be considered at a two time instance. So at time t1, that corresponding data x1, at time t2, that corresponding data is x2. Now, because of this giant density function, we are going to write this one, fx of x1 comma x2 and corresponding t1 comma t2. This t1 is related to x1, this t2 is related to x2 is equal to, so it is a second derivative for distribution function. So dou square by dou x1, dou x2 and probability distribution function fx of x1 comma x2 t1 comma t2. It is the giant density function. Now, this concept, if you want to extend for nth order, if you want to extend this concept for nth order, simply you can write n number of time instants, t1, t2, t3, and so on up to tn in that random variable. Now, that corresponding at time t equal t1, what is the value we are going to get? Is x1 and x2 and so on xn. So these are the giant density functions for nth order, and it is going to be obtained from distribution function. So n number of times we are going to apply derivative here. So that is the relation between density function and distribution function. Now, coming for independent random process concept. This independent random process concept already previously in the giant density function concept also we have giant density function, giant probability density function in the random variable. So that concept we are going to apply here for random process. Previously, we have fxy of x comma y is equal to fx of x, fy of y. So, the joint density function of x and y is equal to individual density functions, product of individual density function in the random variable. The same concept here also we are going to apply for this random process. So again, you consider this joint probability density function. Now it is for nth order fx of x1, comma x2, comma x3, comma and so on xn. Okay. Now that corresponding whatever the density function independent variables probability of A intersection B is equal to probability of A into probability of B. Like joint density function fxy of x comma y is equal to fx of x into fy of y. The similar fashion, now whenever the independent random process at time t1 whatever the x1, at time t2 whatever the x2, at time 3 whatever the x3, that corresponding density functions are independent. We are going to write these all like events, but it is a function of time. So that is the independent random variable concept. Next one is statistical properties of random process. So statistical properties means generally mean value, moments value, and variance. Here generally we are going with mean and moments. The moments we are going to calculate here correlation. Now coming for random process x of t. For this random process x of t, we are going to be calculate mean value. So as usual, mean formula, for random variable concept, whatever the mean formula, that mean formula we are going to apply here. Expected value of x is equal to integral minus infinity x into fx of x dx in the random variable. So the same formula instead of x, we are going to write here is the function of time is equal to expected value of x of t. Now integral minus infinity x into fx of x. This one, it is a different from previous density function. It is this probability density function for random process. Previously it is only x, now extra it is a t. Now we are going to write dx. Next one about moments coming for autocorrelation. So in the autocorrelation, consider the random process x of t, and in that random process, yet two random variables we are considering. The two random variables x1, x2, we are going to be considered at times t1, t2. And we need to, whenever we are considering two random variables, we go for joint density function, joint probability density function. If I write this joint probability density function, fx of x1, comma, x2, comma, semicolon, t1, comma, t2. This t1 related to x1, t2 related to x2. So it is the joint density function for the two random variables in the whatever the random process. The correlation of x1 and x2. The correlation of x1. So the random process is same, but at two different time intervals, we are going to get the random variables. So expected value of x1, x2 is equal to expected value of x of t1 into x of t2. So this x of t1 is at time t equal to t1, whatever the random process. At time t equal to t2, the random process. Now, this expected value of x1, x2 is equal to expected value of x of t1 into t2. It is called, correlation. And because of one random process, it is the autocorrelation. So the autocorrelation representation is R. So because of same random process RXX of first axis for T1, second axis for T2 is equal to expected value of x of T1 into x of T2. Now it is also going to write expected value of x1 x2. Now coming for cross correlation. So the difference between auto correlation and cross correlation is, in cross correlation, we are going to be consider two different random process. Coming for auto correlation, one random process. That is the only difference. Consider two random process, x of t and y of t. We can define the random variable for x of t is x, for y of t is y, and corresponding joint density function is fxy of x comma y t1 comma t2. Now, whenever if we want to write this correlation, it is called cross correlation. Same formula, only thing is instead of x, we are going to get y, t1, t2, x1, y1. You can write here instead of x1, x2, we are going to write xy or x1, y1. That is our choice. fxy of x comma y comma t1, t2 into dx dy. Today I am going to stop this class. We will continue in the next class.